All right, we're going to wrap up the area exploration. I have renamed this region D just so we can keep it separate from the other videos that we did. But I have given you some very different curves here, not the same graph at all. It says find the area of the region, again, we're going to call it D instead of A, bounded by the graphs x equals 3 plus 2y minus y squared, and x plus y equals -1, and the graph is shown below. So they've graphed it. We have a line. We have basically a sideways parabola. And we're going to work through how to find the area of this particular region by going through the steps here. So it says write and solve an equation to determine the points of intersection of the line and the curve. Okay, so we're trying to find the points of intersection here. Well, in the previous example when we did it, both equations were y equals, and so we were able to set what they were equal to each other. Okay, well, we can do the same thing here, but it's going to be really hard to make this bigger one, the sideways parabola, y equals. So I'm going to leave it x equals, and I'm just going to make the x plus y equals -1. I'm going to make that x equals. Okay, so all I have to do to make that x equals is to subtract the y. All right, so these are the same thing. All right, now if these two curves are both, or these two equations are both x equals, then I can set them equal to each other. If they're both equal to x, then I can set them both equal to each other. All right, and that's the equation I'm going to use to solve. Okay, now because of that y squared and the other y's, we're definitely going to have to make it equal to 0. And you want to do it in a way that makes y squared positive. So I'm going to add y squared to the left. I'm going to subtract the 2y, and I'm going to subtract the 3. All right, and you can check behind me. You should get that as your trinomial. And then we're going to factor that trinomial. All right, let's see. We get, what multiplies to 4? So 4, -4, and +1. And so then when I solve, I get +4 and -1. Okay, but those are just the y values of 2 points of intersection. Then I need to find the x values that go with each one of those y values. And that's where it comes in handy to go back to one of your equations that's x equals. And I'm going to do the one that doesn't have a square in it. So let's see, I need -4 minus 1 makes -5. And then when I do negative of -1, I get +1 minus 1, which is 0. Okay, and so then we can label those and see if they make sense. 0, -1, and -5, 4. And if I kind of try to line them up with the graph, those look great. Okay, but I know that those are perfect. Those are exact. All right, now the next one says what interval of x values defines the region. Okay, that means for the region that we've created here, this enclosed region, I want to know what is the furthest x value to the left that would be part of that region. And that's not hard because it's one of our points, -5. But then I also need to know what is the furthest x value to the right. Okay, and it looks like that lines up with 4. All right, so we're going to go from -5 all the way to 4. Those are the x values that this region covers. It definitely doesn't stop at 0 though, right? So we would need to go all the way here. All right, and then number 3 says, 33 says, think of dividing this interval into many subintervals so that we can use rectangles to estimate the area. Will the height of all the rectangles be calculated by the same rule? Okay, if not, why not? Well, that's kind of similar to what we did in the previous example. If we draw the height, all right, over here, if we draw our representative strip all the way over here, then we would be touching the sideways parabola on the top and the line on the bottom. But if we drew it somewhere over here, right, then we would actually be touching the same curve on the top and the bottom. Okay, And so you do have to keep that in mind when you start thinking about dividing up your interval. All right, so we're going to move on to number 34. You can write down what you want from that last explanation. So it says, why is it difficult to write an expression for dA, for our area, as a function x times dx for either one of the regions? Okay, so let's go back to the strip I drew that connects these two. Okay, if I wanted to figure out the length, all right, top curve minus bottom curve. Well, if we did it the same way we did before, you have to be able to solve your equation for y and only have x's in it. And that's not possible for this top curve, okay? You can't solve for y and not have y anywhere else in the problem in this particular curve. All right, and so that's going to be a problem for the first region. It's definitely going to be a problem for the second region because you'd have to do it for the top and the bottom of that curve, okay? And so there are some serious issues there. All right, so as we move on to the next part, it goes on to say that sometimes vertical strips make the problem awkward to analyze, and horizontal strips are more appropriate. Okay, so what I'm saying is we're going to turn our strips horizontally, and we're going to draw our strips across, okay, the graph. All right, and think about it. I'm sure it's going to ask me this in a few minutes, but no matter where I draw that horizontal strip, notice I'm always touching, all right, the same two curves, the same curve on the right and the same curve on the left. So I won't have to divide my region up, which is really good. But the problem is with going horizontal is I'm going to have to change my variable. All right, so it says what interval of y values defines the region. So now I need to know the y values of my region. So what is the lowest y value of my region that I'm trying to find the area of? And then what is the highest y value? Well, that works out pretty nice that I can use my points of intersection, but the lowest y value is -1 and the highest y value is 4. Okay? All right. So again, I was just trying to give you an idea of making our horizontal strips. Now it says divide the interval from problem 10. No, from, interesting. Divide the interval, that means the one we were just talking about, into 10 sub-intervals. Woo, that's going to be a lot of rectangles. All right, the width of each subinterval is not called dx now, it's called dy, okay? And we need to talk about why do we think this is done, all right? And then what is the value of it? Well, it's called dy because we're finding it based on y values, okay? And we want to divide it up into 10 subintervals. And we have to go from -1 all the way to 4. So the easiest way to do that is to take the difference in those two values to see how far apart they are, and then divide it by however many subintervals we want to create. And that ends up being actually 5 divided by 10, which is a half. So when we break this up into horizontal strips of width 1/2, like that ends up being, like, we're going to have to use the 1/2 going, that's how tall they are on the y-axis, okay? And we got to go all the way up to 5. I'm just marking them here, but technically the rectangles are only going to go inside the shaded region. All right, so and again, the reason that it's now called dy is because these are the changes in the y values. All right, so what I want to do is I want to literally draw strips, horizontal strips for each one of these going to try to do, all right, it's kind of hard to be straight, but hopefully you get the idea. Now I do want to stay within the shaded region, even though I'm using those Y values. Okay, and then this last one is just this top corner. All right, so those are my strips, and now it goes on to say, draw the 10 upper edge. All right, so kind of like a right edge, but we're doing the upper edge of the rectangle, and the upper edge will extend from the line to the curve left to right. Okay, so the upper edge, all right, so this first one is literally, there's not really anywhere to draw it. That's the upper edge. And so let's go to, here's this one, and the upper edge will go down like this. Okay, and then the next one, the upper edge is what cuts it off. Then I go down, all right, and then on this one, the upper edge cuts it off here and here. Upper edge. Yeah, okay. So once we get out here, the upper edge actually ends up being a little bit bigger on both. And then this last one's got to go all the way down. There we go. All right, so those are our rectangles. And it says, is the length of each rectangle calculated using the same rule? So would I calculate the length of that upper edge using the same rule every single time? Yes, because I'm touching the same two curves every single time. All right, but instead of top minus bottom, it's going to be right minus left when we start doing it. Okay, it's going to be right minus left. All right, and so the next piece here is just a really big table that has you actually calculating or completing, finding the X values on each one of the, or like on the line and the curve, so each piece of the graph based on the Y value. So we're starting at the bottom Y value and we're working our way up by increments of a half. We're working our way up, all right, all the way to 4. I know it looks like we're going down, but you know what I'm talking about. All right, and we're literally plugging those Y values in to these two equations and getting the X value that goes with it, because that's going to give me the values that I subtract when I do left minus right to get the area, or excuse me, to get the length of each rectangle. So it's just a lot of calculations right now. Technically, if you use your calculator, you basically can, I know it gets confusing, you'd have to switch your X and your Y to use your calculator. So it might be easier if you just kind of work through these one at a time. I'm going to solve this one for X again so that it makes it easier to plug in my Y values. And I'm going to pause the video while I work all of these out, and you should do the same. All right, so you'll want to check your table. Again, what was I doing? I was plugging in this Y value of -1 into each one of these equations and finding the X value that went with it. That's all I was doing. All right, so check your values. All right, if I scroll down too fast, pause the video. All right, because you need to have all of those correct to move on. All right, so now we're going to use those values to literally calculate the area of each of those rectangles, okay? And it really doesn't matter, you know, which way you label them, okay? If we go back to the picture and we want to start down at -1, and we want to call that rectangle 1, 2, 3, 4. We're labeling them up, all right? 8, 9, and 10, okay? If that's how you want to calculate the areas, you certainly can. It doesn't really matter what number they're on as long as you do all 10 of them, okay? And so, of course, I said that, and then I labeled them different on my paper. But if I start with a y value of -1, okay, that's actually not a top edge. That's the bottom edge of the first rectangle. So I'm not even going to use that one at all. I'm going to have to start at the top edge, which is at the -1/2. Okay, so my first rectangle, all right, well, let me change colors so it's easier to read. My first rectangle, all right, remember all of them have a width of 1/2, so we can put that first if you want. And then it's the length that you're concerned about, all right? And you always want to do right minus left, okay? So you got length times width, but when you do length, you want to do right minus left, okay? And then your width for this particular problem is going to be 1/2 the entire time, right? All right, and so when I do right minus left, I'm going to take the 1.75 and I'm going to subtract the -0.5. And you can do the work for that on your own. You get 1.125. And then when I do the second one, my width is still 1/2, but now my length is 3 minus -1, which ends up being 4, and 1/2 of 4 is 2. All right, so hopefully you get the idea. I'm literally just subtracting these two values and multiplying them by 1/2 to get my individual areas. And then at the end, I'm going to add them all up to get my Riemann sum, okay, which is my estimate for the area of these using these 10 rectangles. So I'm going to pause the video here and write everything out, and then you should do the same and then check your work. All right, so I've taken the time to find all 10 of my areas. That last one, which was the top one in the picture previously, ended up being an area of 0, which is why we couldn't really draw it to begin with. And then when I add all of these values up, I get 20.625. So I'm saying my area is approximately 20.625. And we actually already explained this, explained the rule for finding the length. That's what we wrote up here. We did the right minus the left. The right x value minus the left x value. So you can write that down in there if you'd like. All right, and so if I did that, let's write it as a function for the area dA, where we took literally the right x value, but to get the right x value, we had to use the curve x equals 3 plus 2y minus y squared. Okay, so that's the right x value. And then I'm going to subtract the left x value, which was the equation x equals -y minus 1. And that's my length. And to get the area, I have to multiply that by a width, which remember is infinitely thin, so we just call it dy. All right, and so now I'm going to write an integral and actually evaluate it to calculate the actual area. Okay, and so the actual area, all right, is going to be the integral from, and remember, because all of these are y values, you need the y values of the bounds. That's why we found that interval. What y values does this region cover? All right, and you're welcome to simplify this yourself or type it all in as given to you. All right, I will tell you, just to make it shorter when we type it in, I did simplify this down. I combined like terms. I had to distribute my negative and combine like terms. I ended up with 4 plus 3y minus y squared. Now, the catch on this is, even though you have it written as y's on your paper, you can't type it in that way in the calculator. Okay, you do have to change it to x's, and you're just changing it to x's. You're not actually changing the function in any way. You're just using x's to type it into the calculator, because the calculator doesn't care what the variable is. Like, it doesn't matter that it was a y on your paper and now it's an x in the calculator. The calculator can only do x's, okay? As far as I know. Well, let me see, just for fun. What if I did use the alphabet and do 4 plus 3 alpha? Uh-oh, where's the y? Maybe I'm making this too hard. Wait. Oh, there it is. Okay, 3y minus y squared. I'm just wondering, and if I do a y here, will that work? Oh, okay, so it will let you do y's. Huh, interesting. That's a new one on me. And then, of course, we want to do math enter so that we get the exact value, 125/6. But I want to pull my calculator back up because it says, is this value consistent with our approximation? All right, and that's where the decimal comes in handy, 20.833333, and we approximated 20.625, so we were pretty darn good with our approximation. But of course, once you integrate, that is in fact your exact area, okay? So the point of that particular example was that you can't always draw your rectangles vertically, okay? And the key to remember with that is if you have an equation that you cannot get y by itself easily, then you don't want to use vertical strips, okay? If it's much easier to solve for x, then you're going to need to use horizontal strips, and then your interval are going to have to be y values. Okay, that was the purpose of that particular example. And that concludes our exploration on area.